It's Paul Bamberg with the introductory video for Class 12 of Math 117. I've got to warn you, this is very tricky stuff, and I'm not going to attempt to get every line of all the proofs into this short video. In fact, the first time I taught this course, I asked people to be able to prove the monotone convergence theorem, and now I've decided I will settle for having you able to give a complete, accurate statement of the theorem rather than requiring you to prove it. So let's get started. First, we have to talk about events of probability 0. That's a different concept from impossible events, as certain examples will illustrate. The event, you keep flipping a coin up, and it constantly comes up heads, is not an impossible event, but it has probability 0. The probability that this will happen forever is smaller than any positive number. Similarly, if all values of x are equally likely, you pick a random number in the interval from 0 to 1, and the number you get is precisely 1/3. That's an event with probability 0, though it's clearly not impossible. Closely related event, you choose a random number in 0 to 1 and it's rational. That's an event with probability 0. Or in 2 dimensions, you consider a situation where you pick a point at random in the unit square, with all points being equally likely. The event that you happen to pick a point that lies precisely on the line x equals y is an event that's not impossible, but that nonetheless has probability 0. Finally, a really curious one, you choose a real number in the interval between 0 and 1, you look at its decimal expansion, and the numeral 4 never shows up. That's clearly not impossible, but the probability that a random number will have that property is 0. Now, the expectation of a random variable shouldn't be influenced by its behavior on a set with probability 0, and so we're going to introduce the phrase almost surely. Two random variables are equal almost surely if the set on which they agree has probability 1, i.e. if the set on which they disagree has probability 0. So, if we have an integrable random variable x, which happens to equal another random variable y almost surely, then that other random variable y is also integrable, and it has the same expectation as x. The proof of this simply involves splitting off the indicator function for the set on which the two variables disagree, but that set has probability 0, and it doesn't affect the equality of the expectations. A problem that Janines discusses with this sort of almost sure limit is that it's not unique, because we can modify a limit x of omega to which x sub n converges almost surely on a subset of the sample space whose probability is 0, and we're not going to change the fact that the sequence converges to the limit. Of course, we've been talking about a set where two random variables are equal, and we can't talk about that set unless we're sure that it's in our sigma field. Janines addresses this in lemma 6.21, which says that if you've got two increasing sequences of positive random variables on a probability space, then the set in the sample space for which they approach the same limit is guaranteed to be a set that's in the sigma field. I'm going to repeat Janines' proof, but I believe that the best way to read the proof is reading from the bottom of the page to the top of the page. So here goes. We've got random variables x sub n and y sub m from the two sequences, and we know that the difference of two random variables is also a random variable. It follows that the set for which x sub n is greater than y sub m, with the small quantity 1 over k subtracted off, must also be in the sigma field. Now let's take the union of this over all integers n. That is, we're looking at the values of omega for which this is true for any n, and take the intersection over integers y, m, and k. That is, we're considering the case where some x sub n is bigger than this for all the y sub m and all values of k. That is, we're subtracting it off an arbitrarily small number. When we take unions, we stay in the sigma field. When we take intersections, we stay in the sigma field. So the resulting subset is also in the sigma field. But what is it? It's simply the set where the limit, meaning that sooner or later we will find something that satisfies this, is greater than the limit on the other side. Clearly, I can make that same argument reversing the roles of x and y and discover that the subset of the sample space where the limit of the y's is greater than or equal to the limits of the x is in the sigma field, and the intersection of these two sets, both of which are in the sigma field, is also in the sigma field, but the intersection is the set on which the limits are equal. Sigma fields are closed under complements, so the subset of the sample space where the limits are unequal, that's the one we're interested in, is also a set in the sigma field. We've been proving a bunch of theorems, all of which state that if we have two increasing sequences of random variables and they converge to the same limit, the expectation of one converges to the same limit as the expectation of the other. Or to be precise, if we've got increasing sequences x sub n and y sub n, and the limits are equal for every point in the sample space, almost surely, this is what's new, we're allowing them to disagree on a set of measure 0, then the limit of the expectation of the x sub n's is the same as the limit of the expectations of the y sub n's. We've already proved this result for positive bounded random variables without any mention of almost surely. And all we have to do in order to prove this result is to invent the appropriate sequence of bounded random variables. So how are we going to get rid of the almost surely idea? The set on which the x sub n's and y sub n's have equal limits, we've just shown, is an element of the sigma field. We can therefore talk about its indicator function, and we can multiply by that indicator function. In other words, we're just throwing out the part of the sample space where they disagree, but since what we've thrown out is a set of measure 0, we haven't changed the expectation. Now, what we're going to do is create a bounded increasing sequence as we have done before. So we've got x sub n, and we can also create x sub n where all values larger than some integer, which we'll call j sub n, are replaced by that integer. And we can continue to do this, choosing our j sub n's larger and larger in such a way that we make the difference between the two expectations smaller and smaller. We make it less than or equal to 1 over 2 to the n simply by truncating at larger and larger intervals. We can do the same thing for y sub n, and now we've got two increasing sequences of positive bounded random variables. They have the same limits as before, and the expectations also approach the same limits. But we've already proved the key result for bounded random variables. If the pointwise limits are equal, the limits of expectations are equal, and now that result extends to more arbitrary increasing sequences of positive random variables. Now I'm in a position to state the monotone convergence theorem. This is one of the two famous theorems of Lebesgue integration, the other being the dominated convergence theorem, which you'll meet next week. So we've got an increasing sequence of integrable random variables on a probability space. Integrable means the expectation is defined, and what the theorem says is this sequence will converge to an integrable random variable if and only if the limit of the expectations is finite. And furthermore, if that happens, the expectation of the limit is the limit of the expectations. In order to prove this, we've got to think about the subset of the sample space on which the sequence of variables gets larger and larger and larger. So how are we going to do this? We'll pick some positive integer m, and we will think about the subset of the sample space for which the random variable x sub n has a value that's greater than m. As n gets larger and larger, since x sub n is an increasing sequence, this set can only get bigger and bigger. The values are larger and larger, and therefore there could be a larger set on which it exceeds m. And we can talk about the set also for which the limit of x sub n of omega doesn't exist. That is, it's plus infinity. As n gets to infinity, the value of this gets larger and larger. That's going to be in all these sets. If the limit is plus infinity, it will exceed the integer m, no matter how large that integer may be. So this set is a subset of the earlier set for all of the a n comma n, and it's also a subset of the limit of that as n approaches infinity. In a bizarre way, we can prove that this set is in the sigma field. Consider the set of random variables y sub m, which has the constant value m. What is A? A is the set on which the limit of the expectations of x sub n is infinite, but clearly the limit of the expectations of this y sub m is also infinite, and we conclude from that that the limit of the expectation of x sub m is at least as large as m times the probability of the set on which the x sub m's diverge to plus infinity. You look at this and say, that's kind of silly. If this number is not 0, the left-hand side is infinite. That's absolutely right. We're going to consider only the case where p of a equals 0 in our theorem. But first, let's think what would happen if the set on which the sequence of random variables had a limit of plus infinity, diverged to plus infinity, was positive. Imagine in that case that x sub n converged to an integrable random variable on some set B whose complement had probability 0. That is, a set B whose probability was 1. If you intersect a set with another set whose probability is 1, the probability of the intersection can't be 0. It's greater than 0. M is an arbitrary integer, and therefore the expectation of x must be greater than m times the probability of this intersection, and that means that the expectation is larger than any m times some non-zero number, which means that x was not integrable to start with. As I said, that means the only case that's worth considering is the case where the probability of the set A is 0. In that case, while the sequence x sub n has the property that for some elements in the sample space the limit is plus infinity, the set on which the limit is not plus infinity and must therefore be finite is a set with probability 1, or the sequence x sub n converges almost surely to some random variable x, and we know how to write a random variable as the limit of an increasing sequence. We have two increasing sequences that converge almost surely to the same limit. The x sub n's that we get by simply chopping off the values at n, and our original x sub n that converges to the same thing. We're assuming that this limit on the left-hand side is finite, but the limit on the right-hand side is our standard way of defining the expectation of x. This is the canonical sequence we use for x, and that establishes that x is an integrable random variable. Now there's a little trick to creating this sequence. We'll do the usual. We'll divide the image up into intervals that have length over 1 over 2 to the n, and we will also use our usual boundedness trick. If the value is going to be greater than n, we replace it by n itself. Let's let J sub n be the subset in the sample space for which the value is greater than or equal to n. So I can now create a simple positive random variable y sub n, where I have done the usual thing with evaluating at k plus some fraction with 2 to the n in the denominator. And then I have added on n times the indicator function of the set j sub n, where the value is too large to start with. Note this is a kind of diagonalization trick. I'm doing two things simultaneously with n. As n gets larger, I am splitting up the codomain into smaller and smaller subintervals. I'm creating a finer partition, while at the same time I'm pushing up the limit that I use for the upper bound. I can calculate the expectation of this by first taking the expectation of the right-hand side and then adding on n times the probability of this set j sub n, and that defines the Lebesgue integral of this function, and we have so-called monotone convergence theorem. which says, under these circumstances, the expectation of the limit of x sub n is simply the limit of the expectations of the individual x sub n's. Now to finish up, I'm going to describe a cute trick for creating new probability measures from old. You will not understand this fully until you work some examples of it in class, but I'll introduce the idea anyway. Let's consider a positive integrable random variable. It's integrable, so it has an expectation, and I'm going to make that expectation equal to 1. That's not really so severe a restriction. If the expectation came out to be 2, I would simply divide the random variable by 2, and then I'd have one whose expectation was 1. And you can think of this as a sort of probability adjustment function. We can define a new probability measure by saying that the probability we're going to assign to set A is the integral of the random variable x over that set A. That is the Lebesgue integral that defines the expectation of x when we restrict it only to the part of the sample space that's specified by A. A special case of this is the one where the original probability measure assigns equal probability everywhere in the sample space, and in that case you can think of x as behaving like what is commonly called a probability density function. So now we've got a new probability space, same sample space, same sigma field, but a different probability function. And if we have an integrable random variable on this space, its expectation over A is the same as you get by taking x times y and using the old probability measure. That's easy to say. It's not that easy to prove, and I will just state how the proof goes. We've got to show that this new probability measure Q satisfies all the axioms. Why is that going to be so? Well, first requirement is this probability measure has to be positive. That's fine. We integrate x over the set A. Since x is positive, this is guaranteed to be a non-negative number. Second requirement, the probability of the entire sample space has to be 1. That works because of this curious requirement that the expectation of x has to equal 1. Finally, and this is the one that's so hard I'm omitting the details, a probability measure has the property that if you have a set of disjoint measurable sets, the probability of the union of those sets is the sum of their probabilities. This is proved in Janines, and we can conclude by the monotone convergence theorem, though I've left out some steps here, that the new probability measure applied to a countable union of disjoint sets is the sum of the probabilities. It turns out that the converse of this result is much more profound. It's called the Radon-Nikodym theorem. Janines introduces it in chapter 8, and you can actually, in that case, define x to be some sort of derivative of the probability measure Q with respect to the probability measure P. With that brief introduction, I conclude this rather technically intricate introduction.